Today we're going to look at section 7.3, which is estimating a population mean, in which we know sigma, and remember sigma is the standard deviation of the population. In section 7.4, we're going to look at estimating a population mean when we don't know sigma, but for now, we're going to assume that we know the standard deviation of the population when working with this sample size. There's three concepts we're going to look at in this section. First of all, like we did in the population proportions, we should know that the sample mean is going to be the best point estimate of the actual population mean. And like we did in section 7.2, that best point estimate, we don't know if it's a good point estimate or a bad point estimate, but it's going to be the best point estimate we have to find the actual population mean. And thus we construct a confidence interval, again like we did in section 7.2, hoping that we can say with 95% confidence that the actual population mean lies in a certain interval. The second thing out of this section is we're going to learn how to use that sample data and construct a confidence interval that the actual population mean we hope it lies in, and then how to interpret that interval. And the last thing we're going to learn to do is to determine what sample size we're going to need in order to get a good estimate of the population mean. It may be that we want to estimate a population mean. We know a couple things about the population. How big should our sample be so that the results of this section are valid? So before we start to tackle an example here, let's look at some of the notations that we're going to need in trying to develop and trying to come up with this confidence interval. The first notation, and we've done it before, is mu. And remember, mu is the population mean. So that's what we're trying to estimate. When we take our sample, we're estimating where we think mu, the actual population mean, will be. Sigma, that's our population standard deviation. And in this section, we're going to know what sigma is. In section 7.4, we're not going to know what sigma is. And that's probably more realistic, that we don't know the standard deviation of the population. But in order to set up 7.4, we're going to do some examples in 7.3 where we know that population standard deviation. X bar, that's our sample mean. And in our examples, we also call that the best point estimate. N, that's our sample size, or the number of sample values. Big E, if you remember that from the last one, that's our margin of error. And we use technology to find our margin of error for the proportions. We're going to work a couple of these where we're finding the best estimate for the population mean. We're going to work a couple of them by hand. So we're going to actually have a formula for E that we're going to use. And then finally, this is kind of a new one, is a critical value of alpha divided by 2. And you're thinking that's really confusing. We'll show you what that means. That's the z-score separating an area that is alpha divided by 2 in the right, I have to write small here so if I can squeeze it in the right tail of the standard normal distribution. I'll abbreviate that. So z sub alpha divided by 2, that's a critical value. It's the z-score that separates an area, alpha divided by 2, in the right tail of the standard normal distribution. And as we start to apply it and look at it, I think that'll make more sense than just trying to read it here. So now that we have the notation, there are some requirements that need to be met before we can use this. One is that our sample is a simple random sample. Two, that we know sigma, the population standard deviation. And three, if either or both of 1 and 2 are satisfied, trying to squeeze that in again, satisfied, we need to know that the population is normally distributed or that n is bigger than 30. Our sample size is greater than 30. So 30 is kind of our magic number that we're going to work with for our sample size. If it's bigger than 30 and either 1 or 2 are met, then we can use the methods that we're going to talk about here. So those are the requirements that need to be met. Now let's look at the confidence interval. And it's going to look similar, except for the formula for E, which is going to be a little bit different. Like I said, we're going to calculate that by hand. So we're trying to develop a confidence interval in which we say the actual population mean lies between two things. It's going to lie between the sample mean plus our margin of error and our sample mean minus our margin of error. So that's one way to write it. Let's talk about E. The formula for our margin of error is the z-score of alpha divided by 2 times sigma divided by the square root of n. That's going to be our margin of error. So that's the formula we're going to use for finding E. And so our interval, we could also read it as x bar plus or minus our margin of error. Another way to write it is in, looks like kind of an ordered pair, in which the bottom number is our sample mean minus our margin of error, and the top number is our sample mean plus our margin of error. So there's a few ways to write it. I prefer this way, where we write it in interval notation, but a couple other ways you can see it. Sometimes we see it represented in the media like this, and other times we see it written as an ordered pair. But for our purposes, you'll probably see me using the one on top the most. All right, let's look at this z-score of alpha divided by 2. Let's kind of explore what that means. That comes from the normal distribution. Let's say I have a normal distribution here. And I'm going to build a 95% confidence interval. And so that alpha divided by 2, what it really means is that if we're pretty confident that the actual population mean, if we're 95% confident that it's going to lie within this interval, then as we look at a normal curve, 95% of the data is going to fall between here. So that means there's 5% of the data left over to split between the two tails. So our alpha value is basically 1 minus whatever our confidence interval is. And we're going to use 95% more often than not. So our alpha value in this problem would be 1 minus 0.95 or 0.05. That would be alpha. And by dividing it by 2, what we're saying is 0.025 is going to be in this tail, and 0.025 is going to be in this tail. That would mean points that are not within our 95% confidence interval. It could be that when we take our sample, it falls out here, maybe in that tail, or maybe down here. Now, it's not going to happen very often. In fact, it's going to happen very little. But that's where the alpha divided by 2 comes in. What we're looking for is the z-score of this point right here. We want to know what is the z-score that corresponds to this tail having an area of 0.025. And if you go look that up in your table, A2, or you use technology, for a 95% confidence interval, this z-score is going to be 1.96. And the good thing about that is you don't have to look it up every time. When we're doing a 95% confidence interval, this z of alpha divided by 2 for a 95% confidence interval is always 1.96. So that's a number we're going to use quite a bit because we're going to be working with 95% confidence intervals. If it's a 90% confidence interval, then we'd say 1 minus 0.90 is 0.10. We divide that by 2, so the area in each tail would be 0.05. And if we go to our table A2 and look that up, the z-score that would go with that 95% confidence interval, that 0.10, sorry, I'm running in the bottom of my tablet, that 10 divided by 2 is going to be 1.645. So these numbers, it's not like we have to calculate them every time. What we have to understand is what is the size of the confidence interval and what is the critical value that's going to correspond with that. So I'm going to look at example 1 in your book. It's on page 347. It's example 1. And if you want to follow along with me, you can. If you want to turn to that page. But I'm just going to read it instead of writing it all out here. It says, people have died in boat and aircraft accidents because an obsolete estimate of the mean weight of men was used. In recent decades, the mean weight of men has increased considerably, so we need to update our estimate of that mean so that boats, aircraft, elevators, and other such devices do not become dangerously overloaded. Now, using the weights of men from dataset 1 in Appendix B, we obtain the sample statistics for the simple random sample where n equals 40. The mean weight is 172.55 pounds. And it says research from other sources suggests that the population weight of men has a standard deviation of 26 pounds. So what we want to do is we want to come up with, given this sample data of our sample size of 40 and the mean weight of 172.55, and knowing that the standard deviation is approximately 26 pounds for the entire population, we want to come up with an interval let's use a 95% confidence interval for the actual population mean of men. So we've taken one sample and we're going to build a confidence interval where we think the actual population mean is. So the first thing we need to do is verify that the requirements are met. 1, it says it's a simple random sample. We're good there. 2, the value of sigma is assumed to be known, and we said that that's 26 pounds. The next thing we need to look at is our sample size greater than 30. And yes, our sample size is greater than 30. So the requirements are met. So here's what we want to know. 1, what is the best point estimate of the mean weight of the population of all men? Well, that's already answered for us. The best point estimate is always X bar, our sample mean. So for part A in that, find the best point estimate. Well, it's already in the problem. 172.55 pounds. It's the mean weight. B says to construct a 95% confidence interval of the mean weight of all men. And here's where we're going to have to use our formula. Okay, so part B says let's come up with a confidence interval. So the confidence interval, the actual population mean, is going to be somewhere between our sample mean plus a margin of error and our sample mean minus a margin of error. What we want to do is find out what is the margin of error. And the formula for that, if you remember, was the critical value, or the z-score, associated with alpha divided by 2 times sigma over the square root of n. And since we're building a 95% confidence interval, the previous slide showed us that the z-score associated with a 95% confidence interval was 1.96. The sigma in this problem is 26, and our n value is our sample size, or 40. And if we punch all that into our calculator, we end up with 8.0575, all round to 4 decimals. So that 8.0575 is our margin of error. So we're going to need to build our interval. And in order to build our interval, we'll go back to this equation. And we say that the population mean is between our sample mean plus our margin of error, 8.0575, and our sample mean minus our margin of error. And I didn't leave enough room, so we'll squeeze it in there. So if we do our calculations, then our sample mean is going to be somewhere between 164.49 and 180.61. Now, I may have misspoke when I said our sample or our population means somewhere between there. What we're saying is that we say with 95% confidence that the actual population mean is within this interval. It's somewhere in between here. We're not saying that the 95% of the time, remember that was the incorrect one, 95% of the time the population mean falls in here. Not correct. We're saying with 95% confidence, we think the population mean is somewhere between 164.49 and 180.61. So the last question in this example says, what do the results suggest about the mean weight of 166.3 that was used in 1960? So in 1960, it was found that the mean weight was about 166.3. So does that population mean fall within our interval? Well, yes, it does, but it barely falls within our interval. I mean, it's very, very close to the bottom part of our interval. So I think a correct assumption we could make here is, although the population mean from 1960 still falls within our interval, if I were building a canoe, a water canoe, I probably wouldn't want to use this 166.3. What I'd want to do is gather more data and probably find that the actual population mean has increased since 1960. Maybe men are bigger now than they were in 1960. So that's where the interval helps us. Yes, this 166.3 still falls within there, but barely. So I would think maybe we should be updating this population mean that we're using to build our safety requirements. The third key concept out of this section was determining a sample size. And I know we've said in there we need a sample size of at least 30 for us to use the processes that we have in the last couple of slides. But we're going to kind of change it on you. So here's a question. Assume we want to estimate the mean IQ score for the population of statistics students. How many statistics students must be randomly selected for IQ tests if we want 95% confidence that the sample mean is within 3 IQ points of the population mean? So before we get too far, why would we want to know this? Well, what if our sample size was, and we're going to use small, let's say the 6 of you in this class. And we take all your IQs and we find a sample mean. And it may be that because our sample size is small, we find that our margin of error is actually 16 points away from the mean. What we want is, we want to try and find this margin of error that is, this margin of error that is 3 IQ points from the population mean. So in other words, we'll kind of write this out, what we're looking for, and then we're going to use a formula to find it, is we want to know this population mean. We want our sample mean to be within 3 points either side of where we think the actual population mean lies. So we know our margin of error. We know that it's 3. What we want to do is actually try and find our sample size, or we want to find n. What is our sample size we're going to use? And so by deriving the formula for E, we'll go ahead and write it here. It is the z-score, or the critical value of alpha divided by 2, times sigma, all over E. And we want that quantity squared. That's going to give us our sample size. And it comes from a margin of error formula. We just solved the formula for n, and we end up with this formula. So let's go ahead and use the numbers up above and plug them into this formula. For a 95% confidence interval, the z-score that goes with it is 1.96. Our sigma, although it wasn't said in this book, recall what we've done with IQ scores. Do you remember what the IQ, in an IQ distribution, our mean was 100 with a standard deviation of 15. We've done several examples of IQ scores throughout the book. And we want our margin of error in this problem to be 3. And so we're just going to plug this number into our calculator and square it. And when we do that, we get 96.04. Now, this is a sample size. So, do we want to sample 96 students, or do we want to sample 97? Think about that for a second. What we're saying is we need at least this many people in order for this formula here to give us the correct sample size. So if we sample 96 people, that's not enough. So we'd have to round this up. We would need at least 97 people in our sample so that we would say with 95% confidence that the actual population mean would be within 3 points either side of our sample mean. Okay, so we've gone through the process of finding or constructing a confidence interval. We've gone through the process of finding a correct sample size based on what we want for our results. So what I want you working on for the remainder of this class period and into tomorrow, the homework set is on page 353. I want you working on problems 21 through 26.